Okay guys, this is the last part of chapter 14. It's part 5 of acids and bases. Alright, so logarithms. I know most of you have not talked about logarithms in math class yet, but I'm going to kind of briefly go over them. I'm going to go over the part that we use in chemistry. So in chemistry, anytime you see a lowercase p in front of an element, it means to take the negative log of it. Okay? So pH literally translates into negative log of the H. And so this is the formula that we will be using a whole lot. pH is equal to negative log of the H. But before we get into that, I really want to show you what a log is. So log, for you guys in chemistry, is just a button on your calculator. It's short for the word logarithm. And the log of any number is the exponent that 10 has to be raised to in order to obtain that number. So the log of 10 is 1. So 10 is raised to 1 to get 10. Okay, and so the log of 100 is 10 raised to the second power. And that gives you 100. The log of 1,000 is 10 to the third, right? So the log of 1,000 is 3. The log of 0.1 is backwards because 10 has to be raised to the negative 1 to give us 0.1. And the log of 0.01, so you could put this in your calculator and you would get this. Or you could just you could press the button log in your calculator and then put 10 in and it'll give you 1. So you really only have to be able to do the calculations. So in chemistry, we usually only use log base 10. There are other logs that you'll learn about in your algebra class, but we're only going to use log base 10. So there's also log base 3 that's used a lot, and I think log base 7, maybe, I don't remember. But I remember log base 3 for some reason. All right, so what's the opposite of a log? So in chemistry, we usually have to solve equations, and part of solving equations is being able to undo them to solve for your unknown. The opposite of a log is the inverse log, or 10 to the x. So for example, 10 to the third is 1,000, 10 to the negative 1 is 0.1, and I'll show you what I mean by that when we get into the actual chemistry stuff. All right, so here's all the relationships of pH. Now, normally if we were in class, I might derive 1 or 2 of them for you, but I'm not going to try to do that over a video. It'll probably just confuse you. So if we have pH of the negative log of H, and let's say that I wanted to solve for H, then that means that I would have to undo this log. You can't divide by a log. Not a log of no number. You wouldn't be able to divide by the word log. So the way that you undo that, remember 10 to the power of is undoing a log. So first thing I would do is get rid of that negative sign. So I'm going to divide by negative 1 on both sides, or multiply by negative 1, whatever makes you feel happy on the inside. So I have negative pH is equal to log of the H plus, because that negative 1 canceled out the positive on the right hand side. Now I have negative pH is equal to log of H, and I'm ready to undo it. So I'm going to use 10 on both sides. Now that cancels out log. So I have 10 to the negative pH is equal to the H, and that's where that equation comes from. And so these two equations, POH is the negative log of the OH, and then 10 to the POH is the hydroxide concentration. This was from an earlier video, and this equation is derived directly from this. And I'm not going to show you how that's obtained, but it's an easy way to get back and forth between pH and POH. All right, so real quickly, and it's going to be a magic trick for y'all because they're all of a sudden going to pop up after I'm done talking here in a second. I'm going to write down all of those equations here on the right-hand side of the screen. All right, so there they are. And it says calculate the pH, the POH, and the hydroxide of the solution and indicate whether the solution is acidic or basic. So I'm given my H3O, so that's my H. And I want to find the pH, the POH, and the hydroxide. So first I'm going to find the pH because all I have to do is plug that in to this. So in your calculator, and you have to have a scientific calculator, you're going to type in negative log of 1.8 times 10 to the negative 4. And what you end up getting from that is 3.74. So there's my pH, and since the pH is less than 7, that means that this is an acidic solution. Now I also need to find pOH. So using this equation down here, pH plus pOH is equal to 14. So I have 3.74 and plus the pOH is equal to 14. Then I'm going to subtract 3.74 from both sides, and I end up getting 10.26. And then the last part that I need to calculate is the hydroxide concentration. So to find hydroxide concentration, I can either use this or I can use this, because I have both the pOH and I also have the H. I like to use this. It's faster on my calculator. If you have any of the TI calculators, the easiest way to get the 10 that you need is to press the second button and then press the log button. It should be on the left-hand side of the calculator. So up here, you'll see 10 to the negative. That's the one that you want. You don't want to use the E. You want to use the second log, so the anti-log or inverse log button. All right, so if I take 10 to the negative 10.26, I end up getting, for my hydroxide concentration, 5.5 times 10 to the negative 11. All right, so real quick, I want to talk about Sig Figs with logs. With logarithms, the Sig Figs are always only behind the decimal place. So in this number, there's only 2 Sig Figs because it's only behind the decimal place because we took a log to get that number. In this one, there's only 2 Sig Figs. So the reason I only put 2 Sig Figs is because in this number, I only have 2 Sig Figs. So the number that was given to me had 2, so I made sure to put 2 decimal places in any number that I had to take the log of something to get the answer to. All right. This one has 2 Sig Figs because it has 2 Sig Figs, but only 1 decimal place because I didn't need a log to do that one. I had the 2 significant figures from here. All right, so in this one, or calculate the H3O, the pOH, and the OH for a solution with a pH of 4.8. So hopefully you have those equations written down. If you don't, I would go back in the video and record those equations. I'm only going to write down the ones that I'm going to use. I have a pH equal to 4.8, and I want to find the H3O, the pOH, and the OH. So first, the easiest one for me to find would be this, because the relationship of pH and pOH is, if you add them together, you get 14. So if I do 14 is equal to 4.8 plus the pOH, and then I'd subtract 4.8 from both sides, I get that my pOH is equal to 9.20. Now for hydronium, I'm looking for H+, so the easiest thing for me to do would be to take 10 to the negative pH. So that's 10 to the negative 4.8, and that would be equal to 1.6 times 10 to the negative 5th. And then hydroxide, to get that, I'm going to use 10 to the negative pOH. So 10 to the negative 9.2 is going to be equal to 6.3 times 10 to the negative 10th. So this is OH down here, hydroxide, and this is hydronium or hydrogen ion. If you were to multiply those two together, it should round to 1 times 10 to the negative 14 because of this relationship. So there's a couple different ways you can do each of these problems depending on which equations you like to use. I just like to use these. All right, calculate hydroxide, hydrogen ion, and pH for a solution with a pOH of 4.8. So this time we have a pOH of 4.8. Is the solution acidic, basic, or neutral? So first I'm going to calculate pH because we have the pH plus the pOH adds together to give us 14. So the pH would be equal to 9.2. And since the pH is greater than 7, this is basic. And then next I'm going to calculate the H, and that's equal to 10 to the negative pH. So that would be equal to 10 to the negative 9.2. And so after putting that into my calculator, 6.3 times 10 to the negative 10th. And then my hydroxide would be 10 to the negative POH. And that's 1.6 times 10 to the negative 5th. All right, here's two more examples, and then I have a quick couple of definitions for the end of the chapter. All right, what is the hydronium hydroxide pH and POH of a 0.02 molar HNO3 solution? So this is kind of putting together a couple of different ideas here. So this is a strong acid. It would have to be, otherwise we wouldn't be able to determine the hydrogen ion concentration. So since it's strong, that means it ionizes completely. And if we have 0.020 of this, then that means that I'm going to have 0.020 of that when it dissociates, when it splits apart, right? So for every H, there's an NO3. So my H3O concentration, my hydronium concentration, is equal to 0.020. And so next I'm going to go ahead and find the pH, because it's the negative log of the hydrogen concentration. So that would be the negative log of 0.020, and that would be equal to 1.70, which is really acidic, and that's what we would expect to see for a strong acid. Okay, and then next I'm going to find the pH, because the pH plus the POH adds together to give us 14. So plugging in 1.7 for pH, my POH is found to be 12.30. And then my hydroxide concentration, I'm going to find using 10 to the negative POH, and that is 5.0 times 10 to the negative 13. All right, and then the last example problem, I want to know what hydronium, hydroxide pH and POH is of a 2 times 10 to the negative 3rd molar KOH solution. So my hydroxide concentration, because that's a strong base, it would have to be, is going to be 2 times 10 to the negative 13. And so first I'll find my POH, because I just have to take the negative log of that. And that would be 2.70. And then next I'll find my pH, because if I add pH and POH together, I get 14. So plugging POH in for here, I get 11.3. And we expect to find a high pH because this is a base, so we expect it to be higher than 7. And then for the hydrogen ion concentration, I'm going to take 10 to the negative pH, and that gives me 5 times 10 to the negative 12. All right, so I know that these calculations are weird for y'all because you've never done logs, but I promise if you just try to work some of these, it gets really easy really fast, and students tend to enjoy this more than some of the other stuff we do in chemistry. All right, so buffers, solutions that resist pH change. Buffers contain significant amounts of both a weak acid and its conjugate base. So we have some weak acid like acetic acid, and we put in there with it sodium acetate. So that's its conjugate base, because sodium and acetate, this dissolves completely. The sodium ion is a spectator ion, and we have this in solution. So this is the conjugate base of this acid. And the weak acid can neutralize the base, and the conjugate base can neutralize added acid. So it helps us maintain a pH level in a system. And that's what buffers do. They resist pH change for a certain given amount of time. And it's really important in biological systems because then if our blood and stuff wasn't buffered, anytime we drank orange juice, our pH would just drop significantly. So buffers are important. All right, so in the acetic acid solution, the acid will balance out the base added, and the conjugate base here, that part, will balance out the acid. I am not going to have you write these reactions. I just want you to know what a buffer is, as I'm trying to explain it. All right, so here's a picture of what would happen. This is our buffer, this part and this part. And if we add H plus to it, if we add a strong acid to it, we have base here to neutralize it. And if we add base to it, then the acid would neutralize it.